Okay, so I think everyone in this conference room know who Spider-Man is. Well, Spider-Man uses spider web to swing throughout the city. But just like spider webs, spider silk in the real world is just as extraordinary. Spider-Man may use his web to save lives, but I aim to use spider silk to improve the human standard of living. So, good morning, good evening, honorable judge and fellow tripmates. My name is PITCHAYAPA HONGTONG and I'll be presenting the topic of the advancement of spider silk in the medical world. So let's start off with some brief background. So what is a spider silk? It is a filamentous protein, consists of highly repetitive amino acid sequence, and it is produced by the spider abdominal area, which is at the stomach, and by this structure it provided with four unique properties. The first one is biocompatibility, the second one is biodegradable, the third one is antimicrobial, and lastly elasticity and strength. So right now let's take a look at some innovation in the research field right now. So the basic one are of course stitches and bandages, and let's move on to some more advanced operation, which is tissue engineering, nerve repair, artificial ligament and tendon, and lastly drug delivery, which is an implementation of nanoparticle, and this also serves as my foundation of my innovation. So if you take a look at the small bullet point right here, these are the nano tracking system that work. It is very simple methods, and by means simple method give us simple solution, simple results. So my objective is to combine existing knowledge and maximize the features. So this is my innovation. So before I combine my innovation, I would like to explain why we can use the FRET technology right away, because FRET required two dyes, and this means that the nanoparticle inside it is in a very close proximity, causing a disruption to the spider silk as a whole. That's why we have to add a procedure before, which is called the cross-linkable residue, like cysteine. So by adding cysteine, we stabilize the structure of spider silk as a whole. So what if it actually worked? If it actually worked, it would allow real-time monitoring. It also can detect small, tiny changes, as well as high sensitivity for tracking interaction between silk and target molecule, which is good because that's what is going on in the nanoparticle research field, increasing sensitivity and increasing tracking methods. So what to consider? There are two things to consider. The first one is too many cysteine can disrupt the foundation of nanoparticle. As we know, nanoparticle main concept is to be small, but if you add too many cysteine, it becomes irregular in size, causing the efficiency of the delivery to go down. Next is the placement. It matters because the nanoparticle is already as small as it is, and if we are not precise enough, it can disrupt the whole process of drug delivery system. So here is the methods. So the first one, we have to focus on the protein design by adding the cysteine to the protein fragment. Then the second step is we have to activate the FRET technology. And lastly, we use the FRET technology data to analyze the process and the product. And this is what shows if our innovation is proficient enough or not. And over there is a small simple diagram to show the framework of this innovation. So in conclusion, the spider unique property give us a promising material for surgical world and a promising outlook to the medical world. By combining two procedures, we are able to maximize the feature of nanoparticle in real-time monitoring. And lastly, ongoing research can overcome current challenges and move spider silk from an experimental field to a real-world uses. Thank you for listening to my presentation.
혹시 질문이 있으신 교수님께서는 거소해 주시기 바랍니다.
Thank you very much for a nice talk. So I think the problem with spider silk is not, in my impression, is not that strong. So you are saying that you use cysteine to make it stronger?
Actually, the spider silk, it is very strong. It is elasticity and strength is very great due to the sequence of the amino acid. However, we use cysteine because, wait, let me show you this slide. So we use cysteine because we want to apply all the real-time monitoring features. So when we add cysteine to it, so cysteine, it has covalent bond, but the spider silk protein is hydrogen bond. So by adding cysteine, it holds stability of the structure together. So by adding that, we can require 2 dyes and make nanoparticle more effective in real-time monitoring.
Okay.
혹시 또 다른 질문 있으신 분은 거두해 주시기 바랍니다.
So spider silk exists in the form of string, but how do you make nanoparticle using the spider silk?
Well, there's something in the research called hybrid. So spider silk is produced in a very small amount, as we all know. And right now in the research, we have been using only 5 types of spider. So what they do, or the ongoing research, is they did a hybrid synthesis. So they combine yeast or bacteria to make the spider silk more doable in the form. So that's why it changed the structure of the spider silks as well. So from a string, it's like a real material. So there's a hybrid procedure for that in researches.
네, 다른 질문이 없으시면 발표를 마치도록 하겠습니다. 네, 리엄라인 한
Thank you.